We transitioned into the sampling distribution of the sample mean yesterday with the beginnings of with a computer activity. Today we're going to talk about the formulas and how to use those formulas. So the first thing is the mean of the sampling distribution of the sample mean, and that is equal to whatever the population mean is. Okay, then we also need to look at the standard deviation of the sample mean, and to find that you take the population standard deviation and you divide by the square root of the sample size. However, the same conditions still exist with this standard deviation as it did with our one with the sample proportion. This is only true if our sample size is less than or equal to 1/10 of our population. Or if I take my sample size and I multiply it by 10, that needs to be less than or equal to my population size. Remember that this is called the 10% condition. Okay, these formulas are on the formula sheet. Okay, so they will be there, but you need to know what to look for in order to be able to use them. So if we look at this example problem, let's suppose that the number of movies viewed in the last year by high school students has an average of 19.3 and a standard deviation of 15.8. So let's take a simple random sample of 100 high school students. So this gives us our mu, this gives us our standard deviation for our population, and this gives us our n. Let's calculate the mean number of movies viewed by members of the sample. So we're talking about a sampling distribution. So if I take the sampling distribution of x bar and I want to find the mean of the sampling distribution of x bar is just going to be 19.3, the population mean. Okay, for the standard deviation of x bar is going to be the population standard deviation, which is 15.8, divided by the square root of the sample size, which is 100. So that would give me 1.58. I do need to remember to say that we can assume there are more than 10 times 100, which is 1,000, high school students okay, and that takes care of our 10% condition. Okay, we also need to make sure that we really know these symbols very well, the notations. We need to remember that mu here is the population mean, x bar is the sample mean, mu of x bar is going to be the mean of the sampling distribution of x bar, it's whatever's here. And standard deviation with the x bar is the standard deviation of the sampling distribution of x bar, whatever's here. Okay, for proportions, p is the population proportion, p hat is my sample proportion, mu of p hat is my mean of my sampling distribution of my sample proportion, and standard deviation of p hat is the standard deviation of my sampling distribution of my sample proportion. Okay, I need to make sure I know what these 8 symbols mean because they're going to come up again and again and again, and if I don't know what they mean, I won't know how to use them. So let's look at what we actually do with these formulas. Okay, with these formulas, I can use my normal approximations as long as the sampling distribution is normal. However, lucky for us, and like we noticed yesterday, when a sample is taken from a normally distributed population, the sampling distribution is normal, no matter the sample size. Okay, it does not matter the sample size, the sampling distribution will be approximately normal. as long as the population it's taken from is normal. So we need to learn how to differentiate between when I'm working with a sampling distribution and when I'm working with just a population distribution. So let's look at this example. At the Peanutty Peanut Company, dry roasted shelled peanuts are placed in jars by a machine. The distributions of weights in the jars is approximately normal, with a mean of 16.1 ounces and a standard deviation of 0.15 ounces. So without any calculations, let's talk about which of these is more likely. If I randomly select a single jar and find that its contents weigh less than 16 ounces, or I randomly select 10 jars and find that their average content weighs less than 16 ounces. Okay, if I'm just taking one jar, it has the possibility of being any jar in the population. Okay, however, if I'm taking 10 jars and I'm finding the averages, those averages are going to be much less variable than just individual measurements. So what's going to happen is that my jars here are more likely to be closer to the mean, which means the 10 jars, the average of the 10 jars is less likely to weigh less than 16 ounces. So let's look at these actual situations and find the probability to prove our point. So for one, we need to give the variables a name. So we're going to let x equal the weight of a randomly selected jar of peanuts. Okay, since this is just one jar out of my entire proportion, or my entire population, sorry, then I know that x is approximately normal because it's my population with a mean of 16.1 and a standard deviation of 0.15. So I can draw my picture. If my mean is 16.1, I'm looking for what's less than 16. So I'm looking for all of this right here. I need to find my z-score. Z is equal to 16.1 minus 16 divided by, and I just totally did that backwards. It's your x minus your mean divided by your standard deviation. Okay, and I can figure out what that is and then use table A, or I can take my calculator and I can go enter it into normal CDF and type in my lower bound, which would be negative 9999, because I'm going to infinity here. My upper bound would be 16. My mean is 16.1 and my standard deviation is 0.15. And if I type that in, that should tell me my answer, which is the probability that x is less than 16, is about 0.2525. So there's about a 25% chance if I just pick one, it'll be less than 16. Okay, now let's look at the second scenario. The second scenario, our population is not the actual population, it's the sampling distribution. Because since I'm going to say, let's let x bar be the average, weight of 10 randomly selected jars of peanuts, then that means that my population here would be all of the averages of all the different combinations of 10 randomly selected jars. Well, that's a sampling distribution. If we take all possible combinations of size 10 jars and find the means of all of those and then make a distribution out of those, that's the sampling distribution. So what I need to say then is that I need to find the mean. Okay, so the mean of x bar, so the mean of my sampling distribution, is just the mean of my population, so that's going to be 16.1. And then the mean of my standard deviation of my sampling distribution is going to be the 0.15 divided by square root of 10, which is going to give me 0.047. And again, I need to say that we can assume the company makes more than 10 times 10, which is 100 jars. Okay, that takes care of our 10% condition. So I know that X bar here, my sampling distribution, is approximately normal because my population was normal. So the sampling distribution is going to be approximately normal with a mean of 16.1 and a standard deviation of 0.047. Okay, notice that the mean is the same, but the standard deviation is smaller. That backs up our theory earlier because it's going to be centered around the same point, but it's just going to be tighter in. So a smaller proportion will be under 16. So let's go ahead and calculate what that smaller proportion is. Let's say that we are looking for the probability that X bar is less than 16. I need to draw my picture. So there would be 16 colored in. Find my z-score, which is still 16 minus 16.1. But I'm going to divide by 0.047 because that's my standard deviation for this sampling distribution. And I would get the value. And I can then either use table A or again I can use normal CDF and say negative 9999 comma 16 comma 16.1, which is my mean, comma my standard deviation, which is 0.047. And that is going to give me a value of 0.017, or somewhere very close to it. So then I can say, while I have a 25% chance of picking one jar and it being less than 16 ounces, I only have a 1.7% chance of picking 10 jars and their average being less than 16 ounces. So this is clearly the smaller probability and is less likely to happen. It is important that you can see the difference between these two processes. This is if I'm only finding one thing. This is if I'm working with samples. If I'm working with samples, that's when I need a sampling distribution. And that's when I need to use my special formulas for mean and for standard deviation.